Why did the bridge collapse? Any ideas? Feel free to jump in at this point. I guess this is physics 1, so you're supposed to know this.
Wasn't it like the wind made the bridge oscillate with its, and then it just kept going, and it got worse and collapsed?
Okay, Nathan, that's certainly correct. So what do we call that phenomena?
Like it's like a resonant frequency, something.
All right, cool. Give yourself 10 points for that one. So what happens to the bridge? Bridge end up resonating. So the question is, what's resonance and what causes it? And how do you avoid it if you can? So that's one of the questions. The second question is, rock solid. Okay, guys, all these rocks are identical in every respect imaginable, except some of them will ring and most of them won't. So what's the difference between the ringing rocks and the ones that don't? All right, any suggestions? Right or wrong? It doesn't matter, just jump in.
The resonant frequency is the same as the hammer.
Ian, what does that even mean?
Oh,
That was funny.
you said they could be wrong answers.
No, it's not that it's right or wrong. It's like your physics is like a movie physics. It's completely made up.
That's where I learned all my physics.
Yeah, that's fine. So they may have the same resonant frequencies. I'll give you 5 points. That was actually really creative. What else? All right, guys, what else? Is it possible that some of them are hollow? I mean, these things are identical in every single respect. Is it possible that they have different shapes? What do you think is the contributing factor is between the ones that ring and the ones that don't? All right, so whatever your theory is, if you want to jump in, just jump in. Ian's was a little bit too sophisticated for this one. All right, so moving forward, let's talk about waves. So what's a wave? It's a traveling disturbance that carries energy from one place to the next. All right, so number one, it's going to be a disturbance. Well, it's going to be a traveling disturbance, and it's going to be carrying energy with it. All right, so speaking of waves, let's wait for the PowerPoint. Would this be considered a wave? All right, so it's a disturbance, obviously. It's traveling. All right, does it carry energy with it?
Yes.
It certainly does, right? So you have to kind of get back to the definition of energy. So what's the definition of energy? It's the capacity to do work. So it's able to apply a force on something and then make it move along the direction of the force. So this is definitely a disturbance that carries energy with it. It's an awesome demonstration of a wave, as well as why black boxes end up going out of business. All right, pick out the best answer.
B.
B.
All right, so B is the best answer. So, okay, okay, let's go with the best answer. B is the best answer. So, those of you guys who said B, all right, so give yourselves 5 points. And those of you guys who pick B, give yourselves 2 points. Speaking of waves, there are two types of waves that we will focus on. Transverse. Some that wiggles, I'm going to call it a wiggly. It's not the technical term, but I like the term because it's kind of visual. Transverse, you have to kind of look up the definition of wiggly. Everybody knows that something's wiggling. All right. Notice that the wave is moving from left to right. All right, so the arrow indicates the direction of the wave. And you got this point of disturbance, and the point of disturbance goes up and down, 90 degrees to the motion of the wave. So it's going to be perpendicular to the motion of the wave. So the transverse waves, the point of disturbance is going to move 90 degrees to the motion of the wave. All right, so this is a transverse wave. Examples of transverse waves, you're looking at it, you got the slinky. It could be a rope. What else? It could be the electromagnetic waves. What else can you guys think? What else can you guys think of? Sometimes the ocean waves kind of look like that. All right, so those are the transverse waves. Anything that wiggles in that fashion is a transverse wave. Second type of wave, these are known as longitudinal waves, otherwise known as compression waves. I kind of like compression better than longitudinal, but technical term is longitudinal. All right, so once again, the arrow denotes the direction of the wave. And the point of disturbance, which is this, is actually waving back and forth parallel to the direction of the disturbance. All right, so wave is traveling horizontally, and point of disturbance is also vibrating horizontally along the same direction. So point of disturbance is going to be parallel to the motion of the wave. Example of a compression wave or a longitudinal wave is a sound wave. So the sound waves are longitudinal waves. All right, the only reason why we're talking about waves, because the waves can interfere with each other, constructively as well as destructively. We got two approaching pulses. They start to overlap, and then they will reinforce. So what happens to the amplitude when they reinforce each other?
Increase.
Added.
Increases, right? The amplitude is going to get maximized. So this is a constructive interference. So the amplitude, in this case, it actually doubles. And then the waves recede, and then the amplitudes recover. Also, we can get destructive interference if you have two inverted waves. In this case, we got two inverted pulses. When they overlap, and at the moment of perfect overlap, notice that they cancel. The amplitudes will cancel. Or they could become minimized. So waves can interfere destructively or constructively. When they interfere constructively, they will reinforce. The amplitudes is going to become maximized. When they interfere destructively, the amplitudes will either become minimized or they will cancel. So next question is, what is a periodic wave? Periodic wave is, you're looking at, it's a repeating wave. All right, the repeating waves are known as periodic waves, which means that they will go in cycles, predictable cycles. All right, so the repeating wave is a periodic wave, so you're looking at it. So this would be a sine wave. Terminology-wise, we'll need to go over some of the basics. The amplitude is the height of a wave. From a technical perspective, that's going to be the maximum disturbance that the wave is going to undergo. All right, so the amplitude is the maximum disturbance with respect to the undisturbed position, which is right in the middle. And then we have the wavelength. All right, this is a single cycle. This is a second single cycle, the third one, and so forth. So the length of a single cycle is known as a wavelength. All right, you can measure the wavelength from identical points, the midpoint to the midpoint, top to top, bottom to bottom, either way. So these are your wavelengths. The Greek symbol lambda, that stands for L, length, is going to denote the wavelength in this case. Next one is the period. So once again, this is your single cycle. All right, so the time for a single cycle to form is known as period, or time for a single wavelength to form is your period. All right, so single vibration, so for a single cycle to complete itself is known as a period. All right, so the number of periods per second, or number of wavelengths per second, or number of cycles per second is known as the frequency. All right, so here's one cycle, here's a second cycle, here's a third cycle, and so forth. So number of cycles per second is your frequency. All right, so if we have a 1 second time interval ending right here, you would have 1, 2, 3 cycles within one single second. 1, 2, 3, 4 cycles within one single second. All right, that would be 4 hertz. All right, all this stuff is important because I forgot the best answer.
Frequency.
It's going to be frequency. D is the best answer. So give yourself 5 points. The rest of you guys give yourselves 2 points. I'm just curious about this. Who wants to answer it? Right or wrong, it doesn't matter. Okay, Isabella, which one did you pick?
I picked B.
You picked D.
No, B is in boy.
You picked B.
D.
I think it's C.
C.
Or B or C. Okay, that's not bad. Okay, it's either B or C. That's perfect. Okay, I'm actually impressed that you guys kind of remember something from Physics 1. All right, so the question is a couple of things. Number one, wave is a traveling disturbance. Okay, let's focus on the Wiggly's transverse waves. So this is your single wavelength. This is the second one. And here's the third one. So this is a periodic wave, which means that the wave is a repeating wave. So every single cycle is going to repeat itself. So this is the length of a single cycle. This is the time it takes for a single cycle to form. Okay, what else do we have? And this is the amplitude. And then we talked about frequency, number of waves per second. All right, so A is going to be your amplitude. Expressed in terms of meters. Lambda is your wavelength. Once again, it's expressed in terms of meters. T is your period. It's going to be expressed in terms of seconds. Number of periods per second is your frequency. Number of wavelengths per second. Periods per second. All right, so it's seconds per second or hertz. In sciences and engineering, we like hertz, but you can also use seconds per second. It means the same thing. All right, how fast this wave travels? All right, so this is the wave speed. So the speed of the wave can be expressed as a combination of wavelength and frequency. That's it. I'm not going to provide a mathematical proof of it, because you should have seen that in physics 1, but that's fine. Just remember this is a fact because we will need this. Little conclusion until the end of the semester. Okay, so for a given constant speed, all right, I want you to notice that if I increase the frequency, the wavelength is going to diminish. If I reduce the frequency, the wavelength is going to go up. All right, so you have this inverse relationship between frequency and wavelength. All right, so the relationship between frequency and wavelength are inverse. So if that's the case, what's the best answer? All right, so for a given speed means for a given constant speed. So imagine that that speed is constant, so the best answer is going to be, it's going to be C, right? So those of you guys who initially said C, give yourselves 10 points. All right, C is going to be the best answer for that one. Okay, I'm giving you 10 points because we didn't discuss that topic before. All right, so let me ask you this question. Let's talk about sound. How fast does sound travel at room temperature? Simple answer is it travels fairly fast, right? It travels at the speed of sound, which happens to be about 773 miles per hour. Okay, so way faster than a Ford Temple. 773 miles per hour. That's how fast it travels, 773 miles per hour. Did you guys know that the sound travels 4 times faster in water and more than 17 times faster in steel? All right, so why does the speed of sound increase in water and then it increases further in steel? Any ideas? So what determines how fast the wave travels, if that's the case?
The medium.
Yeah, medium itself. Immediately, you notice that the medium itself determines how fast it's going to travel. Give yourself 5 points, guys. So what about the medium that determines how fast it's going to travel? Everything is made up of atoms and molecules. All right, so something about the atoms and molecules. Number one, they will have differing sizes, which means that they will have differing masses. And the molecular connection, they will either be attached to each other loosely or rigidly. All right, so we have to focus on how rigid those connections are. And we also have to focus on the size of these masses. All right, so take a look at these dots that you're looking at. So these are the molecules that you're looking at. And obviously they're connected somehow. Notice that more rigid the connection is, if I were to move number one up in this direction, the second one is going to react to it immediately. So what that means is the larger the molecular tension is, the faster the disturbance is going to move. All right, so that's the first connection that we're making. Looser the connections are, slower the wave is going to move. So more rigid the connections are, faster they will move. Okay, let's move forward. It sounds like Dunkin' Donuts drive-through at this point. Anyway, so more rigid the connections are, the faster the disturbance is going to move. What would happen though if these molecules are really, really massive? All right, so what would happen if I were to increase the mass density? So you have, instead of having small molecules, now you got big molecules. What happens when you apply a force on something which has a tremendous amount of mass? What happens is the acceleration becomes smaller, right? So more massive the molecules are for a given force, the smaller the acceleration is going to be. What that means is these waves are not going to move as fast. So the speed of the wave is going to be directly proportional to the molecular tension, and it's going to be inversely proportional to the mass density. All right, so that's the conclusion that we come up with. All right, so the speed of the disturbance is going to be directly proportional to the tension. T is going to represent tension. And it's going to be inversely proportional to mu. Mu represents mass density in this case. So the density of the medium. All right, so explain this, if that's the case. Which one is a more rigid structure? Which one is going to have a larger molecular tension, water or air?
Water.
Water, obviously, because you got, what is it, 2 molecules, 3 molecules, 2 molecules, H2O, rolling over each other, right? Air molecules are kind of loose. They're not really attached. They're free to move. All right, so what happens to the molecular tension when you go from water to steel? It goes up quite a bit. All right, so molecular tension is going to increase. As the molecular tension goes up, the wave is traveling faster. So that's what it means. Okay, now let's reverse the scenario. Now let's take a look at the relationship between the density and the speed of the wave. Which one is denser? Is it the water or is it the air?
Water.
Okay, so the water density is about 1,000, air is 1.29. Okay, so water is about 1,000 times denser than air. So if that analogy is correct, as the density goes up, the speed of the wave needs to go down, guys. Yeah, it's not happening. So which one is denser? Is it the water or is it steel?
Steel.
Water density is about 1,000. The steel's density is, what is it, 8,600 or something, if I'm correct. All right, so which means that steel is about 9 times denser. So if that analogy is correct, inside steel, it should be moving actually slower than in water. I'm talking about sound. So why is it that the sound travels faster in steel than in water, if that's the case?